Welcome to our Engineers Newsletter Live program on dedicated outdoor air equipment. I'm Jeannie Harshaw from Trane System Engineering Group, and I'll be your host as we examine the various types of equipment used for dedicated outdoor air conditioning. This course is approved by the U.S. Green Building Council for 1.5 continuing education hours toward the LEED Credential Maintenance Program. After attending today's program, LEED professionals may submit their hours to the Green Building Certification Institute. Today's program is also registered with the AIA Continuing Education System and qualifies for Health, Safety, and Welfare and Sustainable Design Credit. AIA members, please provide your member number to your local host before leaving today's session. And professional engineers, check with your state's rules to see if credit for attending today can be applied to engineers' continuing education requirements for your state. If you have questions or comments regarding the content covered today, please send us an email at enl@trane.com. Now, as I mentioned, today we'll examine the various types of equipment used for dedicated outdoor air conditioning. We'll start with a definition of dedicated outdoor air units, then discuss how some of the ASHRAE Standard 90.1 requirements relate specifically to dedicated outdoor air systems. And then the bulk of the program will be looking at specific configurations and types of equipment that can be used for dedicated outdoor air conditioning. Covering this information today will be Trane application engineers John Murphy, Ronnie Moffitt, and Paul Solberg. Now, when planning today's presentation, it became apparent that the term dedicated outdoor air system does not mean the same thing to everybody. So John's going to get us started with a definition.
In our industry, terminology can be confusing. People often use the same term but have different meanings. The term dedicated outdoor air system is no exception. Currently, ASHRAE is in the process of writing a rating standard for dedicated outdoor equipment. So I thought it might be helpful to see how they define it. ASHRAE Standard 920, when completed, will define how to rate the performance of DX dedicated outdoor air equipment. Here's the definition from the current draft of this standard. The key characteristics to note are that the dedicated outdoor air unit is sized to deliver the amount of outdoor air prescribed for ventilation purposes, and that outdoor air is dehumidified to satisfy some or all of the building latent load. Next, a dedicated outdoor air unit is used in combination with a separate sensible cooling system. Finally, it might include a device to precondition the outdoor air before it reaches the cooling coil, and it might include a device to reheat that dehumidified outdoor air. Let's use this schematic to better understand this definition. First, a dedicated outdoor unit is sized to deliver the amount of outdoor air prescribed for ventilation. Now, typically, this is just the minimum quantity of outdoor air required by the building code or ASHRAE Standard 62.1. Second, this unit is used to dehumidify the outdoor air to satisfy some or all of the building latent load. I'll talk more about this in a little bit. And third, it's used in combination with a separate sensible cooling system. In this schematic, these local HVAC units are installed in each space to provide cooling or heating. The unit might include a device to precondition the outdoor air, such as a total energy wheel shown here. And it might include a device to reheat this dehumidified air. Here we show a reheat coil, possibly using heat recovered from the refrigeration circuit. Now, the focus of today's broadcast will be on the different types of equipment used to condition the outdoor air. But first, I want to talk about a few issues that have an impact on the type of equipment used. First, when sizing a dedicated outdoor unit, we need to determine the required leaving air dew point. How dry the unit dehumidifies the outdoor air depends on the application. In some cases, the outdoor air might just be cooled without focusing on dehumidification. Now, certainly this would be the case in a climate that experiences a lot of hot, dry conditions, but this might also be the case in a production type application where humidity is not as much of a concern. One example of this might be a kitchen. In some designs, a dedicated outdoor unit is to provide some cooling to the kitchen while simultaneously providing replacement air for the kitchen exhaust hoods. During warm weather, the dedicated outdoor unit cools the outdoor air to about 70 degrees in this example before delivering it to the kitchen. Again, the primary concern in this application is to lower the temperature in the kitchen a little during hot weather. Not concerned much about lowering the humidity. However, in most applications, the outdoor air is dehumidified to remove the moisture or latent load from the entering outdoor air, and is then dehumidified a little further. In this case, the resulting dew point of the conditioned outdoor air is drier than the space, dry enough so that this ventilation air also removes all of the space latent load. In this case, the leaving air dew point is determined so the space humidity level does not exceed some defined upper limit at worst case conditions. Now I use 60% RH in my example, but you might choose to design the system for a lower or a higher limit. Back in 2001, we produced an E&L broadcast on dedicated outdoor air systems, where we walked step by step through the process of determining the required leaving air dew point. This is a critical step that we often see overlooked. If you are designing these systems, go back and watch that broadcast, or read some of the articles or other publications listed here. They're also listed in your bibliography. They also document this step-by-step process. Finally, some types of local equipment, such as chill beams or radiant cooling panels, cannot handle any condensation. So if this type of equipment is used, the outdoor air must be dehumidified to an even lower dew point, low enough to remove all of the space latent load, plus some margin of safety to prevent condensation from forming on this local equipment. In this case, the upper humidity limit is a 55-degree dew point. This allows water at about 58 or 60 degrees to be sent to the chill beams or radiant panels without condensation. Now, after determining how dry the air must be, the next issue is what temperature the air will be delivered at. Will it be delivered cold or reheated? Many dedicated outdoor air systems are designed to dehumidify the outdoor air and then reheat it to approximately space temperature, sometimes referred to as space neutral. In this example classroom, the dedicated unit dehumidifies 450 CFM of outdoor air to a 52-degree dew point, and then reheats it to about 71 degrees. The local HVAC unit is then used to remove the space sensible load. In this example, the local unit cools 1,380 CFM of recirculated air to about 55 degrees to remove the space sensible cooling load of 2.4 tons. However, when a chilled water or refrigerant coil is used to dehumidify the outdoor air, a byproduct of that dehumidification process is sensible cooling. The dry bulb temperature of the air leaving the cooling coil is colder than the space. If this dehumidified air is then reheated, some of this sensible cooling performed by the dedicated outdoor air unit is wasted. If a space needs cooling, why not make use of the sensible cooling already done by the dedicated outdoor air unit? Now, as Paul will explain in a bit, for a dedicated outdoor air system, ASHRAE 90.1 does not prohibit reheating this air to neutral, as long as it's no more than the minimum ventilation airflow required by ASHRAE 62.1. But even if the reheat energy is recovered, reheating to neutral air isn't usually the most efficient choice. The alternative is for the dedicated unit to dehumidify the outdoor air, but then deliver it at a cold temperature, that is, not reheated. Using the same example classroom, if this 52-degree air is delivered directly to the space, it removes part of the space sensible cooling load. This means that the local unit can be sized for less airflow and less cooling capacity than in a neutral air system. In our example, the local unit now only needs to cool 930 CFM of recirculated air with a capacity of 1.6 tons. This is compared to 1,380 CFM and 2.4 tons for the neutral air system. Looking at it schematically, when the outdoor air is delivered cold at this 52 degrees directly to the space, it removes part of the sensible cooling load in the space. This means that the local unit can be sized for less airflow and less cooling capacity, 930 CFM in this example. However, if the dehumidified outdoor air is reheated to 71 degrees, it removes very little of the space sensible cooling load. In this case, the local HVAC unit will need to be larger, 1,380 CFM in this example. The result is more overall airflow, a total of 1,830 CFM in this neutral air system. This means more fan energy. The dedicated outdoor air unit delivers the same airflow in either case, but the local units in the neutral air system need to move more air. So a dedicated outdoor air system that delivers cold air requires less overall cooling capacity than a neutral air system. The capacity of the dedicated unit is the same in either case, since it's sized for dehumidification load. However, delivering the air cold reduces the required capacity of each local unit. For this reason, a cold air system also consumes less overall cooling energy for much of the year. As I showed, a neutral air system throws away some of the sensible cooling benefit by reheating that dehumidified air. When cold air is delivered directly to the space or to the supply side of each local unit, it removes some of the space sensible cooling load. For those spaces that require seasonal cooling and heating, this means that the local unit can be sized for less airflow than in a neutral air system. The airflow delivered by the dedicated unit is the same in either case, since it's sized based on the summing of the space ventilation requirements. However, delivering the conditioned outdoor air cold reduces the required airflow from each local unit. One caution: if a space requires year-round cooling, the local unit serving that space may need to be sized based on the warmest temperature that will be delivered by the dedicated outdoor air unit. Now, while the dehumidified air should be delivered cold whenever possible, as the space sensible cooling load decreases, this cold outdoor air may provide more cooling than the space requires. As a result, the space temperature can drop. Looking at our same example classroom, the design space sensible cooling load is just under 30,000 BTUs per hour. The 450 CFM of outdoor air, when delivered cold at 52 degrees, provides 10,740 BTUs per hour of sensible cooling to the space. This is 36% of the total design load. This means that the sensible cooling load in the space has to drop to less than 36% of the design load before this cold outdoor air will even begin to overcool the space. Until that happens, deliver the air cold to avoid the energy waste of recooling at the local units. Why reheat to neutral on the hottest days of the summer when all spaces need cooling? Now, in hotel guest rooms or dormitories, where the sensible loads are often drastically different in various spaces throughout the day, there may be more hours when overcooling can occur. For these applications, it might just be simpler to deliver the dehumidified air at a neutral temperature. But in classrooms or offices, space-sensible cooling loads are relatively high during daytime hours. In fact, for some climates, classrooms may never reach the point where overcooling occurs during occupancy. These applications are typically well suited for cold air. So what do you do when overcooling finally does happen? Well, first, consider implementing demand control ventilation. By reducing the outdoor airflow delivered to the space when there are less people in that space, you may avoid this overcooling altogether for some applications. Next, the HVAC unit serving the overcooled space could just activate its local heat to prevent this overcooling. If this occurs in only a few spaces, the sensible cooling benefit of delivering the outdoor air cold to all those other spaces may outweigh the heating energy needed for these few spaces. Or if this is a water source heat pump system, when only a few heat pumps are operating in the heating mode to prevent overcooling by the cold ventilation air, this situation likely improves system efficiency. As the heat pumps operating in the heating mode extract heat from the water loop, they reduce the amount of heat that must be rejected by the cooling tower, saving heat rejection energy. And all the other heat pumps, those that are still operating in the cooling mode, continue to benefit from the sensible cooling provided by the cold outdoor air. At some load condition, however, it might be more economical to reheat the dehumidified outdoor air centrally using recovered energy. In this case, design the system to deliver the air cold and only reheat when needed to avoid overcooling the space. A very simple control approach would be to activate the reheat coil only during the colder months of the year. or whenever the outdoor temperature drops to the point where the sensible loads in some of the spaces are low enough that the cold outdoor air is expected to cause overcooling. For example, maybe you activate this reheat coil whenever the outdoor temperature drops below, say, 65 degrees. Of course, this limit could be changed by trial and error after a few months operating the system. Alternatively, a building automation system can monitor the temperature in every space that's served by this dedicated outdoor air system and look for that one space where the temperature is closest to its heating set point. That's the space at most risk of overcooling. Based on this signal from the BAS, the dedicated outdoor unit can then increase its reheat capacity, resetting the leaving air dry bulb temperature upward just enough to prevent that coldest space from overcooling. If an application has very high space latent loads or requires a lower than normal space dew point, the outdoor air may need to be dehumidified to a very low dew point. In this case, the air temperature leaving the coil may be colder than the HVAC design engineer is willing to discharge directly into an occupied space, say below 45 degrees, for example. In this case, the dehumidified outdoor air might be reheated to a more traditional supply air temperature, such as 55, but certainly not reheated all the way to neutral. Finally, if the conditioned outdoor air will be delivered to an open ceiling plenum near the intake of each local unit, the dehumidified air might need to be reheated to avoid condensation. In this case, it's a good idea to reheat the dehumidified air to a dry bulb temperature that is well above the expected dew point in that ceiling plenum. The last issue is how the conditioned outdoor air will be delivered to the individual spaces. 4 common configurations are direct to each space, to the intake of each local HVAC unit, to the supply side of each local unit, and to the ceiling plenum near each local unit. Now, we don't have time in this broadcast to discuss the advantages and drawbacks of each, so we've included supplemental slides at the end of your handouts.
Beyond providing the appropriate air conditions to the space, we need to do it in an efficient manner. As we were preparing this broadcast, we ran into several questions about how some of the ASHRAE Standard 90.1 requirements relate to dedicated outdoor air systems. So, in this next section, Paul will cover a few of these requirements.
Paul? There are 5 key requirements of ASHRAE 90.1 that affect the design of dedicated outdoor air systems. They are minimum equipment efficiencies, fan power limitation, economizer requirements, exhaust air energy recovery, and limitations on simultaneous heating and cooling. Let's investigate each of these. There currently is no rating standard nor certification program covering DX dedicated outdoor air equipment. Therefore, 90.1 does not include a minimum efficiency requirement for these products. However, ASHRAE is working on this and is developing Standard 920 to fill this gap. Next, to determine how the 90.1 fan power limitation affects dedicated outdoor air units, we first need to look at the definition for a common phrase used in 90.1, and that phrase is fan system. This slide shows the definition of fan system brake horsepower. In short, it's the sum of all fan horsepower that is used to move air to or from the space. This example from the 90.1 User's Manual further explains that the dedicated outdoor air fan horsepower must be apportioned to the space or spaces to which it supplies air. In this example, an elementary school uses 8 water source heat pumps, each with 3/4 horsepower fan motors. A 5 horsepower fan in a dedicated outdoor air unit is supplying 500 CFM of outdoor air to each classroom. And the question is asked, does this comply with the fan power limitation? The answer helps define the term fan system. Each heat pump is a separate fan system because each has a separate cooling and heating source. And the power of the dedicated outdoor air system fan must be allocated to each of the heat pumps on a CFM weighted basis. So 1/8 of the 5 horsepower fan in the dedicated outdoor air unit is added to the fan horsepower of each water source heat pump. When we do this, the total horsepower for each fan system is 1 3/8. Since this is under the 5 horsepower threshold for this section, this system does not need to comply with the fan power limitation. From the example, we can infer that the definition of fan system is all fans which support air movement to or from the heating or cooling source, including ventilation and exhaust. If the total horsepower for the fan system exceeds 5 horsepower, then that fan system must comply with one of 2 options. Option 1, the design shall not exceed a maximum fan system nameplate horsepower, or option 2, the design shall not exceed a maximum fan system brake horsepower. The standard includes equations for each option. There are exceptions. One is that individual fractional horsepower exhaust fans do not need to be included in the calculations for either option 1 or option 2. Also, and perhaps the most important, is that the fan systems 5 horsepower or less are exempt. This will exempt a number of dedicated outdoor air system applications, as the previous example showed. Next, let's discuss the implications of the requirement for an economizer. As part of the prescriptive requirements, ASHRAE 90.1 requires that each cooling system that has a fan shall include either an air or water economizer. There are a number of exceptions. Most notable is exception A, which limits the requirement to fan cooling units 4.5 tons or greater, and only in some climate zones. Even after apportioning the dedicated outdoor air capacity to the capacity of the local HVAC units, many cooling systems will be smaller than this threshold, making them exempt from this requirement. If an economizer is required, a designer can select from a number of potential system configurations. First, the dedicated outdoor air system could be oversized to allow for the extra CFM. Second, an additional air path may be created to deliver 100% airflow for economizing. Both of these may be pricey options. Third, for fan coils or radiant cooling, a water-side economizer back at the chiller plant may be the easiest answer. And fourth, one could use the energy cost budget method rather than follow the prescriptive requirements of 90.1. Now let's look at what 90.1 requires for exhaust air energy recovery. In the 2010 version of 90.1, the requirement for exhaust air energy recovery depends on the climate zone and the percentage of outdoor air to design airflow CFM. This will require energy recovery in more systems for many climate zones. Within this section is a definition of energy recovery effectiveness and requires that 50% effectiveness be achieved. 90.1 defines effectiveness as a change in enthalpy equal to 50% of the difference between the enthalpies of the outdoor air and return air. In this example, the outdoor enthalpy is 41.3 and the return enthalpy is 28.5. In this case, the energy recovery device must reduce the entering air enthalpy to 34.9 BTUs per pound or lower. Be careful here. This definition is different than how AHRI Standard 1060 defines the term effectiveness. Here is the equation used by Standard 1060 to certify the performance of energy recovery devices such as wheels. Note that m dot outside air is the mass flow rate of the outdoor air, and m dot min is the lesser of the outdoor air or exhaust mass flows. If these two flow rates are different, meaning that you have less exhaust airflow than outdoor airflow, this effectiveness equation will result in a different answer than the definition of effectiveness used by 90.1. Bottom line is that a device with an AHRI certified effectiveness rating of 50% may not provide the 50% enthalpy reduction required by 90.1. Let's take a closer look at that. Here's an example with unbalanced exhaust and outdoor airflow. A device that achieves a certified effectiveness of 50% does not meet the 90.1 requirement of a 50% enthalpy reduction because of the unbalanced airflows. A device with more surface area would be required. Don't confuse the applied effectiveness required by standard 90.1 with rated effectiveness, which is certified performance by AHRI 1060. An air-to-air heat exchanger with unbalanced airflows requires more surface area to meet the as-applied effectiveness required by 90.1. To minimize the heat recovery exchange area, try to bring back as much exhaust air as possible. An often unused source of that exhaust air is from the restrooms. Restroom exhaust can be used for energy recovery and may need to be used to better balance the outdoor air and exhaust airflows through the device. This is a schematic of a system we have done which ducts the restroom exhaust back to a central point and mixes it with the building exhaust immediately upstream of the energy recovery device. Through exception, ASHRAE 62.1 allows restroom exhaust to be used for energy recovery as long as the transfer, carryover, or leakage of this air is no more than 10% of the resulting outdoor air intake flow. This leakage measurement is part of the certified performance available through ASHRAE Standard 1060, so it is readily available. The last 90.1 requirement we'll look at is related to reheat. When a dedicated outdoor air unit dehumidifies the air and delivers it at a cool temperature, we may eventually become concerned about overcooling the space. ASHRAE 90.1 does not allow simultaneous cooling and heating, so what about reheat? Well, if the amount of air being reheated is no greater than the minimum ventilation rate required by ASHRAE 62.1, then reheating is allowed. This is confirmed by an example in the 90.1 User's Manual that specifically discusses how this requirement applies to a dedicated outdoor air system.
Thanks, Paul. You know, something mentioned when putting this broadcast together was how helpful the 90.1 User's Manual can be. It answers a lot of these interpretation questions and is full of examples. Next, we're going to get into specific configurations of equipment that can be used for dedicated outdoor air conditioning. John?
There are multiple configurations and possibilities for dedicated outdoor air equipment. Which configuration is the best choice for a specific project depends on the goals of that project. Ronnie is going to discuss several questions that need to be asked and answered to help define what is needed from this equipment.
What I've seen in my years of experience with these systems is that the primary drivers that determine the configuration of the dedicated outdoor air unit can be defined by answering these 4 questions about how the unit is to fit in the overall system. First, what's the dehumidification duty of this unit? That is, how dry does it need to be to dehumidify the air? Second, what's the cooling duty? There will be separate equipment in the space to maintain space temperature. How much can the space cooling load be removed by the dedicated outdoor air unit? Third, what's the efficiency target? Does this system just need to meet the minimum energy code, or do you want it to be more efficient? And finally, what's the source of cooling energy? Where will the heat be rejected, and what is available, and what could be available? The goals and requirements of your project should define what your dedicated outdoor air equipment looks like, not the other way around. That is, the dedicated outdoor air equipment should not define what your system looks like. This is no different than any other aspect of building or HVAC design. Let's look at each of these 4 goals a little further, starting with dehumidification. As previously discussed, a dedicated outdoor air system by definition accomplishes dehumidification work. So the first question to ask is how much dehumidification is required from the equipment. This will indicate on how dry the air needs to be. That is, what is the required dew point of the air leaving the equipment? This pie chart shows the sources of water vapor, or latent loads, for a typical K through 12 classroom. The latent load from the ventilation accounts for almost 2/3 of the total. The remaining 1/3 is space loads, mostly due to people and infiltration. The more densely populated the space loads will be a larger portion of the total latent load. Typically, the goal of dedicated outdoor air unit is to control the humidity in the space, but sometimes this isn't the goal. The goal might just be to make sure the outdoor air is not introduced to the space untreated. In this case, the outdoor air is dehumidified to the desired space dew point, removing only the latent load due to ventilation. It's not dehumidified any further to remove space loads. In this case, the space latent loads must be removed by the local cooling equipment. Here are some space dew points for various relative humidity targets. At 75 degrees dry bulb, 50% RH equates to a dew point of about 55 degrees. So if you want to design the dedicated outdoor air unit to dehumidify the air to 55 degree dew point, the space will not be at 50% RH. Any space latent loads will raise the humidity level above this. The resulting humidity level in the space is at the mercy of how much the space sensible equipment is running, and if it is removing any moisture at that time. If the heat pump or fan coil is operating to remove a sensible cooling load, it might be removing some moisture too. You can control the dedicated outdoor air unit based on the measured space humidity to try to help out, but if the original goal was to only remove the ventilation load and not introduce untreated ventilation air when the space humidity is high, then the equipment might not have enough capacity to lower the humidity level. To prevent this, in many cases, the goal of the dedicated outdoor air system is to control the humidity in the space. This means the dedicated unit is designed to remove not only the latent load from the ventilation air, but also the space latent loads. Then the local units only need to remove the space sensible loads. As John explained, to remove the space latent loads, the dedicated outdoor air unit needs to dehumidify the air to a dew point that is drier than the space. How dry depends on the desired indoor humidity level, the outdoor air flow rate, and the space latent load. This chart approximates the required dew point. Assuming a space load of 200 BTU per person per hour and a space temperature of 75 degrees, we can calculate the leaving air dew point required to remove this latent load using various outdoor air flow rates. For example, if the maximum space humidity is 60% and the ventilation rate is 13 CFM per person, the dedicated outdoor air unit will need to dehumidify this air to 51 degree dew point to remove all the space latent load. If we want a drier space and a maximum limit of 55% RH, the air would need to be dehumidified to 47 degree dew point. As I showed with the pie chart, there will also be a space latent load due to infiltration. This would increase the space load and require an even lower dew point from the dedicated unit. The shaded regions on this chart give you a feeling for the range required, depending on how much infiltration there is. Next, we can overlay the required ventilation rates for some typical applications. This gives us an idea of how dry the air needs to be. For an office using the default occupancy density suggested by ASHRAE 62.1, the ventilation rate would be around 17 CFM per person. With a 55% RH limit, the leaving air dew point of 50 or below may be needed. For a school classroom with 13 CFM per person, a dew point of 47 or below may be needed. And for a lecture hall with 8 CFM per person, the leaving dew point might need below 40 degrees to remove all the space latent loads from the dedicated outdoor air equipment. So in this case, the dedicated outdoor air unit dehumidifies the air to a dew point that is drier than the desired space conditions, dry enough to also remove all the space latent loads and control the space humidity. The supply air will be drier down here in the shaded region of the chart. Sometimes the goal of the dedicated outdoor air unit is to dehumidify the space far enough to prevent condensation at the local HVAC unit, or to meet a specific humidity requirement for some process. An example of this is when chilled beams or radiant panels are being used for space cooling. In this case, the dedicated outdoor air unit is designed to remove both the ventilation load and the space latent loads. Well, in this case, it dehumidifies the air to a dew point that is dry enough to keep the space dew point below the surface temperature of these devices to prevent condensation. In the case of radiant cooling or chilled beams, the space dew point is kept below the chilled water temperature delivered to these devices. This defines the first piece of the puzzle to help determine the type of equipment required. What is the dehumidification duty? The next building block or goal that needs to be defined is what is the cooling duty of the dedicated outdoor air unit? Should it be delivered neutral temperature, removing only the ventilation load and providing no space cooling? Or should it deliver the air cool to remove some of the space sensible cooling load? Or should it deliver cold air and remove as much of the space load as possible? With neutral air, the dehumidified outdoor air is reheated to a dry bulb temperature that is about the same temperature as the space. In this case, the local cooling equipment is relied on to remove all of the space sensible cooling load. As John explained, this will lead to bigger space equipment and could result in extra fan energy for the system. As we mentioned earlier, an alternative would be to dehumidify the outdoor air to the required dew point, and then deliver it cold, without reheating it at all. In this case, the cold, dry ventilation air removes a significant portion of the space-sensible cooling loads, allowing the local cooling equipment to be smaller and use less energy. This will allow the space equipment to be downsized as much as possible. Somewhere in between neutral and cold is cool air. In this case, the dehumidified outdoor air is still delivered at a temperature that is cooler than the space, removing some of the space-sensible loads. However, sometimes there may be a limit on how cold the air can be. For instance, if the conditioned outdoor air will be delivered to an open ceiling plenum, that air should be reheated to a dry bulb temperature that is higher than the dew point within that plenum to prevent condensation. Or in applications where the required dew point is very low, the design engineer may want to reheat the air up some before delivering it directly into occupied spaces. This defines the second piece of the puzzle. What is the cooling duty? The third goal is the efficiency target. Does the equipment need to just meet the minimum requirements or local energy code of ASHRAE 90.1? Or do you want to optimize the dedicated outdoor air equipment for the specific application and obtain a higher efficiencies if possible? And the final piece of the puzzle is what cooling sources are available for the given project. Is there a chiller plant that can serve the dedicated outdoor air equipment, but is also used to serve the local equipment in the space? Is installing a dedicated chiller an option? Or does this need to be direct expansion equipment? If there's flexibility here, the other three goals will probably drive this decision on the cooling source. If there isn't flexibility and the source of cooling is dictated to you, then this could be the primary driver in the equipment configuration, as we'll discuss later. What affects all these goals is the financial constraints of the project, as with any other part of building design. If one design option has a higher installed cost than another, does it have an acceptable return on the investment? The most important factor in this is to consider the various costs of the entire system, not just a dedicated outdoor air unit by itself. A more expensive dedicated unit may allow for the lowest overall system installed cost. And vice versa, the lowest cost dedicated outdoor air unit may result in the highest system installed cost. This relationship can also be true for lifelong operating costs.
Ronnie, if we just consider these four goals, you can come up with 54 unique combinations to influence the configuration of the dedicated outdoor air equipment.
And these aren't the only factors. There may be requirements related to acoustics or air cleaning, or the project might have architectural constraints. But I found these four questions will help direct the decisions for the dedicated outdoor air equipment.
You know, what this emphasizes to me is that there's no silver bullet solution for every application. The right equipment configuration for one project may not be the best choice for another. Now let's look at some different configurations, starting with what you might call the minimum duty dedicated outdoor air unit. That's a unit that dehumidifies the outdoor air to just remove the latent load due to ventilation. We'll assume this unit delivers the dehumidified air at a cold temperature, allowing the space-sensible cooling equipment to be downsized. And as Paul mentioned, to meet ASHRAE 90.1, exhaust air energy recovery will likely be required for many applications. In this case, when the unit is dehumidifying to remove only the ventilation load, not to remove space latent loads, this can typically be done with a 55-degree leaving coil temperature. Either DX or chilled water can do this, so the cooling source probably is not critical here.
In this example configuration, a 70% effective energy wheel preconditions the entering outdoor air, reducing the load on the cooling coil by 47%. Then the cooling coil dehumidifies to 57 degrees. With a 57-degree leaving cooling coil temperature, this unit's required cooling capacity is about 240 CFM per ton. This CFM per ton and this supplier dew point can be provided by most packaged or applied dehumidification equipment. Let's look at the psychrometrics of this unit. The outdoor air enters and is pre-cooled and dehumidified by the energy wheel. Then the cooling coil dehumidifies the air down to 57-degree dew point. to the target space humidity level. The fan adds a few degrees of heat, and this air is delivered to the spaces. This air will be cool enough to remove some of the space-sensible cooling, but it will not be dry enough to remove any of the space latent loads. Based on the chart I showed earlier, if this is a classroom we wanted to keep the space below 55% RH, the dedicated outdoor air unit would need to provide 46-degree dew point air to remove all the space latent load. In this case, with the outdoor air being delivered only at 57-degree dew point, the actual relative humidity in the space will be higher than 55%. If there is no space-sensible cooling load in the space, the local equipment will not be removing any moisture, and the resulting relative humidity will be 71%. This might be the case at part load conditions. At design conditions, the space equipment will likely remove some of the latent load, so the space relative humidity will be between 55 and 71% when cooling is needed.
As we discussed, if you want to dehumidify the space, the dedicated outdoor air unit will need to deliver air at a dew point that is drier than the space. In this next unit configuration, we'll assume the unit dehumidifies the outdoor air to a dew point that is dry enough to also remove the space latent loads. We'll assume the dehumidified air is still delivered at a cold temperature and stay with a code minimum unit for now.
This example configuration is the same. It contains an energy wheel and a cooling coil. The difference is the leaving coil temperature. The wheel preconditions the outdoor air, reducing the coil load by 35%. Based on my earlier chart, 46-degree dew point is in the typical range to keep the classroom below 55% RH. What cooling sources could work for this application depend on how densely populated the space is and the space latent loads. For a chilled water system, the closest reasonable approach between the leaving air temperature and entering chilled water is 4 degrees. So here we would need 42-degree chilled water or colder. Most packaged DX equipment is not designed for this low of a dew point, so that option may be limited, especially considering the capacity required for this example is 175 CFM per ton. Here's what the process looks like. Outdoor air enters and is pre-cooled and preconditioned by the energy wheel, reducing the load on the cooling coil. To remove all the space latent load, the cooling coil is cooled all the way down to 46-degree dew point. This air will be cool enough to remove some of the space-sensible cooling loads and dry enough to remove all the space-latent loads. In cases where the conditioned outdoor air is delivered to an open ceiling plenum, this air needs to be reheated above the dew point of the air in that plenum to avoid condensation. A common example might be a school with a ceiling-mounted water source heat pumps. In our example, 75 degrees dry bulb and 55% RH equates to a dew point of about 58 degrees. So the 46-degree dew point air leaving the cooling coil needs to be reheated to above 58 degrees. For those who want room neutral air, the air would be reheated to something like 70 or 75 degrees. In either case, even if this heat is recovered from the condenser or for some other source, this reheat will not be free, as it also comes with a cooling cost. For every 12,000 BTU per hour of reheat added in the dedicated outdoor air unit, it will add a ton of cooling to the overall system. This may also add to the fan or pumping energy for the system, because the space-sensible cooling equipment may now need to provide more cooling. For this cool and reheat system, the process is similar. Outdoor air enters and is pre-cooled and preconditioned by the energy wheel, and then dehumidified down to 46-degree dew point. The air is dry enough to dehumidify the space, but colder than desired. So the reheat coil warms it to 58 degrees. A 10,000 CFM unit, this is 135,000 BTU per hour of reheat, which adds 11 tons to the overall cooling capacity of the system.
Let me toss in one more consideration here. Whatever equipment type is used, consider a configuration that allows dehumidification during unoccupied times. Historically, temperature and humidity have been controlled during occupied periods, but allowed to drift when the building is unoccupied. But some facilities may need to consider dehumidification during the unoccupied period to reduce the risk of microbial growth or damage to building materials or furnishings. The ASHRAE handbook specifically addresses this concern for school classrooms during the summer. A current trend, especially in climates that experience humid weather, is to limit indoor humidity at all times, even during unoccupied periods.
To John's point in the example configuration I showed earlier, you may have noticed this extra damper. This allows for the recirculation of return air for humidity control after hours. It would typically be closed whenever the building is occupied, so the unit conditions only outdoor air required for ventilation. But if the indoor humidity level gets too high during unoccupied periods, the unit can turn on and this damper opens to recirculate air from the indoors. The unit then dehumidifies this recirculated air and then reheats it if necessary to avoid overcooling the spaces. Let's return to the unit with the energy wheel. When the wheel preconditions the entering outdoor air, it helps reduce the load on the cooling coil, but it doesn't help with the cooling energy wasted by overcooling and then reheating. If you want to limit this wasted cooling energy, one option to consider is using a recovery device in series. In this configuration, outdoor air passes through the upstream side of the series heat exchanger, where the air is pre-cooled by the air leaving the cooling coil. Then the cooling coil dehumidifies the outdoor air to the desired 46-degree dew point. Finally, this air passes through the downstream side of the heat exchanger, where it is reheated by the heat recovered from the air passing through the upstream side of the heat exchanger. This series device could be an air-to-air fixed plate heat exchanger as shown here, or it might be a coil loop or a heat pipe. If you need to reheat the air and deliver it cool rather than cold from a dedicated outdoor air unit, using the series heat exchanger is an alternative method of meeting the energy recovery requirements of ASHRAE 90.1. Let's look at the series unit on the cycle chart. On this example design day, if all the air went through the heat exchanger, it would overheat the supply air. So in this case, 75% of the air bypasses around the exchanger. The 25% that goes through the exchanger is pre-cooled to 67 degrees, which also results in condensing of 44 pounds of water vapor per hour. This pre-cool air mixes in with the bypassed air. Note this series heat exchanger will require a way to capture and remove this condensate. For an example 10,000 CFM unit, more than 5 gallons per hour will be condensing on the upstream side of this exchanger. For this reason, a sensible only heat wheel would not be used in this configuration, since it cannot handle the condensate removal. Then this mixture is dehumidified by the cooling coil to our 46-degree dew point. This cold air then passes through the downstream side of the heat exchanger to be reheated, recovering the heat that was removed from the entering outdoor air. At this design condition, the face and bypass dampers modulate how much air passes through the heat exchanger to achieve the desired 58-degree air leaving the unit. In this example, the pre-cooling reduces the load on the cooling coil by 13% at design. This is compared to 35% reduction in the unit with the energy wheel. However, this reduction in cooling tons will occur for every hour that the outdoor air temperature is above 64 degrees, while the amount of energy recovered by the energy wheel will be much less at a milder outdoor air condition.
While he showed a fixed plate heat exchanger in the example, Ronnie also mentioned that a coil loop or heat pipe could be used. This chart compares the heat recovery effectiveness of these 3 devices when each is selected for a ½ inch pressure drop per pass, or a total of 1 inch pressure drop in this series configuration. Each has a high enough effectiveness to reheat the 46-degree dew point air to 58 degrees at design conditions. But when the entering outdoor air is cooler, supplemental reheat will be needed at some point. How much depends on the device. The heat pipe with a 40% sensible effectiveness will need to add supplemental reheat whenever the outdoor dry bulb is below 76 degrees. The coil loop has a little higher effectiveness at 50%. It will require supplemental reheat whenever it's colder than 70 degrees outside. The fixed plate heat exchanger has the highest effectiveness at 65%. It won't require supplemental reheat until it's cooler than 64 degrees outside. So it's important to compare the effectiveness, pressure drop, and cost of these different devices, and to understand how this performance difference impacts energy use at part load conditions, not just design conditions.
In my example with the series sensible exchanger, I mentioned that pre-cooling the air, the heat exchanger reduced the design cooling capacity of the dedicated outdoor air unit by 13%. That was compared to dehumidifying the air to 46 degrees with a cooling coil alone, without any energy recovery. If both systems are required to reheat the air, to 58 degrees in this case, then this savings will reduce the installed cooling capacity for the overall system. For this example, 10,000 CFM unit reduces the required capacity by 11 tons versus a cool reheat system delivering air at the exact same conditions. But what if you don't need to reheat this air to 58 degrees? What if the cool reheat unit delivers air cold, at 48 degrees in this case, without reheating it? The unit with a series heat exchanger still requires 13% less capacity in the dedicated outdoor unit, or 11 tons less. But these 11 tons are just shifted from the dedicated unit to the equipment out in the spaces. The 48-degree air delivered by the cool reheat unit removes more of the space-sensible cooling load, allowing for the local equipment to be smaller. Even though the dedicated outdoor air unit requires 11 tons more capacity, the local equipment requires 11 tons less. So for the overall system, there is no net difference in the installed cooling capacity. This series heat exchanger still may be preferred for some applications, since it delivers the air at a temperature above space dew point. It also keeps the space equipment operating in the cooling mode for more hours of the year, which might be beneficial for a geothermal system.
As we've mentioned, if a goal for the dedicated outdoor air system is to reheat the dehumidified air to a neutral temperature, it will require the local cooling equipment to handle more of the space-sensible load. When a series heat exchanger is used, how much the local equipment is impacted depends on whether or not the series device has a means of capacity control.
If there isn't a bypass on the heat exchanger, the air would leave the unit at 80 degrees in our example. Either the space-sensible cooling equipment will need to be oversized, or the unit will need to be equipped with a bypass. Applications for this type of configuration are limited. This might be used in a dormitory or hotel where conditioned outdoor air is delivered to the corridor. For this neutral air application, all the outdoor air passes through the upstream side of the heat exchanger, where it is pre-cooled to 71 degrees and condensing out 85 pounds of water per hour for this 10,000 CFM unit. Then this air is dehumidified by the cooling coil to our 46-degree dew point, dry enough to remove the space latent loads. Finally, the air passes through the downstream side of the heat exchanger, heating it up to 80 degrees. This pre-cooling reduces the cooling load on the dedicated outdoor air unit by 31 tons, or 35%. This is about the same capacity reduction as a unit with an energy wheel. However, the air is delivered at 80 degrees, while the energy wheel unit could deliver it at 48 degrees if needed. In this case, since the dehumidified air is reheated and delivered warm, this 31 tons of capacity is just shifted out to the sensible cooling equipment.
Again, either a fixed plate heat exchanger, coil loop, or heat pipe could be used in this manner. But of course, delivering the dehumidified air at a neutral temperature requires more reheat, so supplemental reheat will be required more often. In fact, if the goal is to reheat the dehumidified air to 75 degrees, both the heat pipe and coil loop will need supplemental reheat all the time, even on design day. Because it has a higher effectiveness, the fixed plate heat exchanger can recover enough heat on the hottest days. But even it will require supplemental reheat when the entering outdoor air drops below 90 degrees.
The decision on whether to use a parallel configuration, like the unit with an energy wheel, or a series configuration, like the unit with a series heat exchanger, depends on the goals and limitation of the project. For the majority of applications, the parallel configuration will be the best fit. This is because the exhaust air is typically available for recovery, and delivering the air cool and cold results in a larger reduction in the overall system capacity. However, there are applications where the series configuration might make more sense. if there's a need for neutral temperature air and there is no recoverable source of reheat energy, this might be a good choice. Note that it might take analyzing a couple operating points over the year to decide which works best for the application at hand.
Restrictions on the cooling sources available for a given project may also drive the decision to use a series configuration, but it might require using a series desiccant wheel rather than a sensible heat exchanger. As an example, if the system requires 46-degree dew point air from the dedicated outdoor air unit, what can we do if the only source of cooling on the project is a central chiller plant that makes 45-degree water? A cooling coil can't make 46-degree air if it only gets 45-degree water. An alternative is to use a Type 3 desiccant wheel in series with the cooling coil. This can also meet the prescriptive energy recovery requirement of ASHRAE 90.1.
For our example, the 45-degree chilled water can be used to obtain 52-degree air leaving the cooling coil. Then the air passes through the downstream side of the series desiccant wheel, where the water vapor is removed, drying the air to our 46-degree dew point. Sensible heat is released during the process of absorbing the water vapor, so the air is heated to 58 degrees dry bulb. As this desiccant wheel rotates, it's regenerated by the entering outdoor air upstream of the cooling coil. Here the desiccant releases the water vapor into the airstream, raising its dew point temperature before it passes through the cooling coil. The cooling coil modulates to maintain the desired leaving air dew point. As entering outdoor air conditions vary, the leaving air dry bulb temperature may fluctuate a few degrees. But since there is a separate sensible equipment to cool or heat the space, this is usually not an issue. For this process, it's easiest to start looking at the air leaving the cooling coil. Air leaves the cooling coil near saturation. At this high RH, the desiccant will have a high affinity for water vapor, so water vapor is absorbed from the airstream. This lowers the dew point from 52 to 46, while raising the dry bulb temperature from 52 to 58. The moisture and heat then are transferred to the incoming outdoor airstream. The outdoor air is at 48% RH, so the desiccant will have much less affinity for water vapor. The water vapor absorbed on the process side will be released on the incoming airstream, where it will then be condensed out by the cooling coil. Because the cooling coil does not need to dehumidify the air all the way to a 46-degree dew point, this configuration reduces the required cooling capacity by 13%. And since the process of the absorption raises the temperature of the air, it also saves 12 degrees of reheat needed to warm the air back up to 58 degrees. Both of these savings are the same as what the series air-to-air heat exchanger provided. The big difference between the two is that the series desiccant wheel does this with a 52-degree air leaving the cooling coil, while the series heat exchanger required a 46-degree leaving coil temperature. This can result in significant energy savings, as it will raise the evaporator temperature of the cooling source by 6 degrees, increasing the efficiency of either a chiller or DX system.
Even if there isn't a restriction on the available cooling source, you might still choose this series desiccant wheel configuration for other reasons. One might be efficiency. Using a shared water-cooled chiller plant will likely be more efficient than using an air-cooled DX unit operating at a very low suction temperature. Another application might be a system that uses radiant cooling panels, or for a process, where the same chiller plant is being used for both the dedicated outdoor unit and the space cooling or process equipment. The series desiccant wheel will allow the dedicated unit to deliver air at a dew point that is lower than the chill water temperature.
Note that if neutral air is desired with this configuration, a reheat coil will be required to reheat the dehumidified air. As we've discussed, this will shift more of the sensible cooling load to the local equipment, increasing the installed cooling capacity of the overall system. The main driver in this desiccant process is the difference between the outdoor air relative humidity and the relative humidity of the air leaving the cooling coil. At the example condition I showed, the outdoor RH is low enough to regenerate the desiccant. But when the RH of the entering outdoor air gets high, like on a mild rainy day, preheat will likely be needed to lower the relative humidity of the incoming air. As Paul mentioned, if the dedicated outdoor air system delivers only the minimum ventilation air required, this preheat is allowed by ASHRAE 90.1. Let's revisit the parallel versus series discussion using the series desiccant wheel rather than the sensible heat exchanger. Again, the decision depends on the goals and limitations of the project. If the choice for achieving the required dew point is between lowering the chilled water temperature delivered by the central plant or using a series desiccant wheel, the series arrangement will likely make more sense. But the series wheel is not just for applications that require a very low dew point. It really is a matter of how low the required dew point is versus what temperature you have available from the cooling source, or what it costs to go colder with the cooling source. Like I said before, you should analyze a couple of operating points over the year to decide which is the best for your application.
We've talked about several configurations that all meet the minimum prescriptive requirements of ASHRAE 90.1. But what about going beyond and seeking higher efficiency?
If cool rather than cold air is required, multiple recovery devices can be used. Shown here is a coil loop added to the unit with an energy wheel and cooling coil. This second downstream device is used to reduce reheat energy. The coil loop recovers sensible heat from the warm exhaust air and uses it to reheat the cold dehumidified air. In this example, a 50% effective coil loop is adequate to reheat the 46-degree air to 58 degrees. Based on the examples John showed earlier, the less effective heat pipe would not be able to reheat the air all the way, so you would need supplemental reheat or a heat pipe with more surface area and a larger pressure drop. The fixed plate heat exchanger would have enough capacity and could also be used here. Notice as the coil loop recovers heat, it also cools the exhaust air. This cooler exhaust air results in more energy exchanged by the wheel, saving more cooling energy. Let's take a look at this two-stage process on the cycle chart. Outdoor air is pre-cooled and dehumidified by the energy wheel. Because the coil loop has an effect of pre-cooling, the exhaust air, the energy wheel transfers more energy and reduces the cooling load by 45% compared to 35% with the wheel alone. The cooling coil dehumidifies the air down to the 46-degree dew point, and then the coil loop reheats the air from 46 up to 58 degrees. Since the temperature of the exhaust air remains relatively constant year-round, the benefit of the second device, the coil loop in this case, will remain relatively constant. Of course, the benefit of the energy wheel will be less at off-design conditions. Because the exhaust air is 75 degrees, it is impossible for the second device to reheat the dehumidified air all the way to 75 degrees. That would require a 100% effective energy recovery device. However, with a 65% effective fixed plate heat exchanger, it's possible to reheat the air up to 68 degrees. Then fan heat would add a couple more degrees after that. A 70% effective energy wheel and a 65% effective plate exchanger will reduce the load on the dedicated unit's cooling coil by 53% versus a straight cool and reheat unit. A better way to look at this is that an energy wheel reduces the load by 37%, and the plate exchanger shifts 16% of the design load to the space equipment.
Note that a sensible heat wheel would have similar performance to the plate heat exchanger. But in this example, the 65% effective plate exchanger cools the exhaust air to the point where water vapor begins to condense out of that exhaust air. For a 10,000 CFM unit, it condenses 3 gallons of water an hour. Since a heat wheel is not designed to handle condensate, it's typically not recommended for this purpose.
An alternative is to use a passive desiccant wheel, and to use this passive desiccant wheel in a downstream parallel location. The passive desiccant wheel will lower the dew point leaving the unit, something the sensible heat exchanger cannot do. This allows the cooling coil to operate at a warmer temperature, 51 degrees in this example, compared to 46 degrees with a sensible exchanger. This warmer coil temperature improves cooling equipment efficiency. It may also allow for an existing central plant to be used without needing to lower the chilled water temperature. and without needing to install a separate chiller. Again, if neutral air is required, a reheat coil would be required. In this configuration, the more heat transferred by this downstream device, the less moisture can be transferred. So if neutral air is required, a parallel plate exchanger might be a better choice, unless the cooling coil is unable to achieve the required dew point. For this dual path, dual wheel unit, outdoor air is pre-cooled and dehumidified by the energy wheel. Then the air is dehumidified by the cooling coil down to 51 degrees. And finally, the air passes through the desiccant wheel, which further dehumidifies the air to our 46-degree dew point. This absorption process releases some sensible heat, warming the air to 55 degrees dry bulb. An equivalent to 9 degrees of reheat energy is saved, and cooling capacity is reduced by 41%. On the other side, the exhaust air regenerates the desiccant, which cools and humidifies the air. This air then passes through the exhaust side of the energy wheel. The pre-cooling of the exhaust improves the sensible cooling benefit of the energy wheel, but since the desiccant wheel added moisture to the exhaust air, the dehumidification benefit of the energy wheel is lessened. Since the condition of the exhaust air remains relatively constant year-round, the benefit of the downstream desiccant wheel will remain relatively constant. On this example, mild rainy day, the amount of reheat and cooling saved by this downstream wheel is about the same as the design day, but the benefit of the energy wheel will be less at off-design conditions. Notice how the outdoor and exhaust air conditions are much closer to each other, so the amount of energy recovered by the energy wheel is much less than on the design day.
A concern with this arrangement is that the downstream desiccant wheel in the parallel arrangement depends on exhaust air getting back to the unit to regenerate the desiccant wheel. If there is minimal exhaust flow, maybe less than 80% of the outdoor airflow coming in, then the performance of this parallel desiccant wheel will drop off greatly, and you may not get the dehumidification you desire. Air that leaks out of the building due to positive pressurization and air leaving through local exhaust fans decreases the exhaust airflow coming back to the unit. And if demand control ventilation is used to reduce intake airflow, the central exhaust airflow must also be reduced to avoid negative building pressure. For some applications, there may be little or no centralized exhaust airflow to regenerate the desiccant, which renders it ineffective.
For that reason, a better arrangement might be to configure the desiccant wheel in series to minimize this risk. Here, the regeneration side of the desiccant wheel is located in the outdoor airstream, upstream of the cooling coil. Outdoor air is first preconditioned by the energy wheel, then passes through the upstream side of the series desiccant wheel. The cooling coil modulates to maintain the desired dew point, leaving the unit. And the passive desiccant wheel allows the unit to deliver the air at a dew point lower than the coil can achieve on its own. Again, if the neutral air is needed, a reheat coil would be required. Here's the dual wheel unit with the desiccant wheel in series. Outdoor air is pre-cooled and dehumidified by the energy wheel. Then the air passes through the upstream side of the series desiccant wheel, picking up water vapor that has been removed from the air downstream of the cooling coil. The cooling coil dehumidifies the air to 52 degrees. And then the air passes through the downstream side of the desiccant wheel, which further dehumidifies it to our 46-degree dew point, while warming it to 57 degrees dry bulb. An equivalent to 11 degrees of reheat energy is saved, and cooling capacity is reduced by 44%. As with the parallel configuration, the benefit of the desiccant wheel will remain relatively constant year-round, while the benefit of the energy wheel will be less at off-design conditions. And unlike the unit which had the series desiccant wheel without an energy wheel, preheat is not needed to regenerate the desiccant when outdoor RH is high. On this example, mild rainy day, the energy wheel transfers moisture from the entering outdoor air to the drier exhaust air. This lowers the relative humidity of the air entering the upstream side of the series desiccant wheel, low enough to regenerate the desiccant without any preheat. Here's a comparison of the two downstream desiccant wheel paths, parallel and series, on the same chart. On this design day, you can see the paths are different, but the end results are very similar. Both achieve the desired dew point at about the same leaving air dry bulb. As it was for the units with a single recovery device, deciding whether to use a parallel or a series configuration is not always clear. The series arrangement will save more cooling tons on the hottest design day and during the warm weather. The parallel arrangement will save more tons on cooler days when it's still humid enough to require dehumidification. In most cases, however, the difference in annual cooling energy for parallel versus series will likely be small, within about 2%. If enough exhaust air is available for regeneration and there are a lot of hours of humid weather when it's below 60 degrees outside, the parallel configuration will be slightly better. If there are more hours of hot weather, then the series configuration will be slightly better. However, in most applications, performance on design day and during hot weather is most important, since this is when the load on the cooling equipment is the highest and when efficiencies are lowest. Saving 3 more tons on a day when it's 95 degrees outside may be more beneficial from an energy perspective than saving 9 more tons on a 60-degree day. To summarize, the parallel arrangement for this downstream desiccant wheel will perform better during mild, humid weather, while the series arrangement will perform better during hot and warm weather. If the unit will be installed inside with horizontal through-the-wall duct connections, then the parallel arrangement may allow for a smaller footprint. For roof-mounted installations, the series arrangement may allow for a smaller footprint. And series will be better if the ratio of exhaust air to outdoor air flow drops. This might happen when building pressure is actively controlled or if demand control ventilation reduces intake airflow during partial occupancy. Finally, if the external static pressure is high, the downstream wheel in the parallel arrangement will result in a significant amount of conditioned outdoor air leaking into the exhaust air, which is wasted energy.
Ronnie commented a lot about how the cooling source can impact the configuration of the dedicated outdoor equipment, whether a shared chiller plant or dedicated chiller will be used, or whether the equipment will be DX. Paul, let's put a little more focus on that last square in our puzzle.
The top part of this chart depicts the dew point that the dedicated outdoor air unit must deliver to maintain indoor humidity at either 50 or 60% RH. This assumes that the dedicated outdoor air unit removes the entire space latent load, requiring the local units to provide only sensible cooling. As Ronnie explained with his chart, this is a range because ventilation rates and space latent loads vary by application. The bottom part of this chart depicts the typical range of dew points that can be achieved by the various types of equipment. So the cooling source used might be influenced by the dew point required. The need for even drier air may necessitate the use of a specialty mechanical or desiccant dehumidifier. Let's start by discussing packaged and split DX configurations and then follow with chilled water configurations. There are system design decisions which shape the configuration of a DX dedicated outdoor air unit beyond that of just being packaged unit or a split system, compliance with standard 90.1 being one of them. Another is the choice of heat rejection sources, either air-cooled or water-cooled. For example, if the space equipment will be water source heat pumps, the water loop may be a good choice for heat rejection. If there is no water loop, then an air-cooled condensing unit or similar is likely choice. Another consideration is that reheat may be necessary at times. It seems obvious that air forcibly cooled shouldn't be reheated any further than necessary to prevent overcooling of the space. This may require a higher level of control. The cost associated with the proper control of a dedicated outdoor air unit can be offset by limiting the use of reheat and taking credit for the sensible cooling provided by the outdoor air unit and downsizing the local equipment. There are advantages and disadvantages to either packaged DX unit or split DX system. The obvious advantage to a packaged product is that it's a pre-engineered, whereas the split is typically a local design. A local design can be optimized for the specific application, but the package unit will be lab tested and its footprint is probably smaller if the split uses outdoor products. Refrigerant line length is always an issue for splits and often needed requirement for both hot gas bypass and reheat make the number of lines, length, routing, and cleanliness important factors to the success of a split system. The cooling load on a dedicated outdoor air unit varies from near zero capacity when the outdoor air conditions are close to set point to needing full capacity when at design conditions. The need to unload refrigeration capacity to reasonably match the load is important both for efficiency and maintaining acceptable space conditions. All of the compressor unloading technologies listed here have limitations. Some cannot unload low enough, and others need special sequencing or parts when unloaded to guarantee that oil returns to the compressor. The special sequence is something the compressor manufacturer provides. This is typically only for variable speed or greatly unloading compressors. The other compressor technologies will probably need hot gas bypass to maintain temperature and humidity control. Hot gas bypass can prevent coil icing and is a means by which the refrigeration capacity of a system can be reduced to better match the load. ASHRAE 90.1 allows hot gas bypass to be used, but only in a limited amount. During hot gas bypass operation, the compressor must be loaded at a higher level of compression than the resultant refrigeration effect. This is necessary so that hot gas bypass can trim the unneeded refrigeration effect and match the load. But the trim portion of the refrigeration effect is wasted energy and makes the system run at abnormal head and suction pressures. Abnormal pressures can also occur when the refrigerant heat recovery or hot gas reheat is used. For example, when outdoor conditions are cool but humid, the load is small. But cooling is still required for dehumidification purposes. Any of the compressor technologies with or without hot gas bypass can provide too much capacity and deliver the air cooler than desired. So to prevent overcooling, reheat must be added. The challenge is in the design of the heat recovery system so that it operates reliably when the system is likely under the simultaneous abnormal operating pressures of hot gas bypass. One consideration may be to minimize the reheat coil capacity and deliver the air as cold as possible. Another is to actively control head pressure. Remember, in a split system, to pay particular attention to oil management. Oil does great things in the compressor, but does little good anywhere else. For a split system, the selection of the cooling coil is important for efficiency and stable operation. This chart shows EER and capacity versus design saturated suction. It clearly shows improvements in both EER and capacity as the saturated suction temperature increases. All systems will work at design load, but what happens when the load falls off below the minimum stage of the compressor? If the coil is selected at low suction, then hot gas bypass will be required to operate sooner to try to stabilize the coil temperature. Remembering that hot gas bypass is not an efficient way to unload, it's easy to see that a system selected at higher suctions that doesn't so quickly need hot gas bypass to operate will use less energy. Having said this, we can understand the value of a package unit where selection and testing of the reheat, hot gas bypass, and cooling coil have been done by the manufacturer. Probably the most flexible type of dedicated outdoor air equipment is a water chiller, or water-to-water heat pump, connected to an air handler. In some cases, this might involve using a standalone chiller serving one or more dedicated outdoor air handlers, or the building might have a shared chiller plant that serves both the dedicated outdoor air handlers and the local cooling equipment, as might be the case with fan coils. This may be an air-cooled chiller or a water-cooled chiller that is connected to the water distribution loop. With this equipment configuration, the air handling unit may be installed indoors or outdoors. Typically, chilled water is capable of delivering drier air than most DX equipment. And a chilled water air handler is capable of operating over a wider operating envelope than a DX system, partially because of the water loop acts like a buffer. This buffer is a great benefit if demand-controlled ventilation will be used, since this results in varying airflow across the coil while simultaneously controlling the wide range of entering air conditions. Another benefit of using chilled water for the dedicated outdoor air unit is greater flexibility and an opportunity for even higher levels of efficiency. For instance, Hot gas bypass may not be required on a chiller if the loop time is long enough to overcome any potential stage change. And since a chilled water loop is being used, it opens up the possibility of using thermal storage to shift the load and reduce energy costs. Also with the chiller, you get ASHRAE certified performance, so you're sure to get what you paid for. There's currently no ASHRAE certification program for DX dedicated outdoor air units. Finally, using a chiller will typically result in a lower refrigerant charge than a DX unit. This can help achieve LEED EA credit 4. In cases with a shared chiller plant, oftentimes the water temperature is not cold enough for the dedicated outdoor air unit to reach the required leaving air dew point. In that case, a standalone DX unit might be installed, or a booster DX coil might be installed in series with the chilled water coil. However, it may be easier and more reliable to add a booster chiller or a water-to-water heat pump to provide the colder water required. This schematic depicts a water-to-water heat pump connected to the water distribution loop in a water source or ground source heat pump system, but it could be a central chilled water plant. This heat pump can provide cooling or heating to one or more dedicated outdoor air handlers. Or this could be a small air-cooled chiller used to cool the water from the central plant to the temperature needed by the dedicated outdoor air units. The advantage of an air-cooled chiller is in the simplicity of the piping and control, but the heat pump heating is lost. Whether a heat pump or chiller is used, consideration must be given to freeze protection of the water coils. Another advantage of using a water-to-water heat pump connected to the loop is that the cooling and heating equipment can be distributed throughout the building, often located very close to the dedicated outdoor air unit that it is connected to. For example, in this high school, a dedicated outdoor air handling unit might be located to serve a wing of a classroom, such as the middle wing on the left-hand side colored gray. The water-to-water heat pump might be installed in a small closet in the wing to minimize the cost of piping and ductwork.
We packed a lot into this broadcast, but hopefully you can use the 4 primary goals that we discussed to analyze the options on your next dedicated outdoor air system project. Remember, it all starts with determining what leaving air dew point is required. Do you need just to remove the ventilation load, or do you want to also remove the space latent load? Can you take advantage of the cold, dehumidified air to remove some of the space-sensible cooling load, or do you want the air reheated to neutral? Do you just want to meet code, or are you striving for higher levels of efficiency? And finally, what cooling sources are available on the project? Do you have a central plant? Can you install a dedicated chiller, or will DX equipment be used? As John mentioned, there's no silver bullet solution to every dedicated outdoor air application. There are a lot of options from packaged DX units to split systems to air handlers that are connected to a dedicated chiller or a shared central plant. The equipment type and configuration that's best for a given project depends on the project goals and available budget. The right equipment configuration for one project may not be the best choice for another. Thank you to our 3 presenters for putting this program together. Now, there are a number of publications available that provide more information on the material covered today, including several engineers' newsletters, application manuals, and articles. A bibliography detailing these resources is available from your local site coordinator. As mentioned earlier, an on-demand version of the past DNL, Dedicated Outdoor Air Systems, is available along with a number of US GBC approved LEED continuing education courses, free of charge. So visit trane.com/continuing education for a complete list. Additionally, past DNL program DVDs are also available to order. Visit trane.com/ENL for a complete list. Finally, we're excited to announce our 2012 Engineers Newsletter Live program lineup. In spring, we'll be back to provide insight on the impact of ASHRAE Standard 189 2011. In June, we'll discuss heat pump systems. In fall, we'll discuss technologies used for air-to-air energy recovery. So please plan on attending. Thanks for joining us today. We'll see you next year.